Hi all, let's take a look at a couple of problems here in section 4.3. The first one's pretty quick and straightforward. We're asked to find the critical points of the polynomial function 6x squared minus 7x minus 21. Automatically, since it's a positive parabola, you know any critical point that you do find will be the minimum vertex, since this is going to be a U-shaped function. I take the derivative here. Derivative of 6x squared is 12x. Of course, derivative of minus 7x is just minus 7. I take that derivative equal to 0 to find the critical points. When I do that, 12x would equal 7, and thus x is going to equal 7 over 12. Now, at that point, I set up the first derivative sign test. What the first derivative sign test is going to do is break up the domain of your original function with this critical point. So we test from negative infinity to 7 over 12, and from 7 over 12 to infinity. I know this critical point is the only place at which my first derivative could change sign from positive to negative, and thus my original function could change from increasing to decreasing. So in order to test that, the numbers between negative infinity to 7 over 12, I'm representing with 0. It's in that interval. The numbers between 7 over 12 and infinity, I'm representing with a 1, which is certainly in that interval. Now, I choose these test points and I plug them into my first derivative. When I plug a 0 into that first derivative, clearly I get a negative 7. The only thing I care about is negative. Anytime the first derivative is negative, that tells me that my original function is decreasing on this interval. When I test the 1 to look at the second interval, I can see that it would be a positive 5. Again, the only thing I care about is that it is positive, which tells me that my original function is increasing from 7 over 12 to infinity. And thus, if you're decreasing before 7 over 12 and increasing after 7 over 12, you know 7 over 12 is the location of a minimum. So now I go back to my problem and it says, find the x coordinates of the critical points that correspond to a local minimum. Well, that's my 7 over 12 here. So I'll minimize this and do my fraction 7 over 12. For the next one, critical points that result in a maximum. There are no maximums in this function. Does not exist, D and E. And then we can say, for my next one, the function is increasing. Well, again, remember, the function is increasing whenever the derivative is positive. The derivative is positive from 7 over 12 to infinity. So I can go in here and say it's increasing between 7 over 12 and then infinity here. Whoops, you got to make sure to get out of the fraction first, comma, infinity. And then we can say, okay, for my next one, it would be decreasing whenever the first derivative is negative. And notice the first derivative is negative between negative infinity and 7 over 12. So I'll do my parentheses, negative infinity, up to the fraction 7 over 12, and we got it. I'll check that answer, and it's saying correct. Now, the next one that was asked here in this section was number 13, so I'll scroll down to it. The number 13 here, the work that I have to show for it, I'll put like this. I can say I'm looking at the fourth degree polynomial function, 5/4 x to the fourth plus 20 over 3x cubed minus 45 over 2x squared minus 180x. So it's wanting you to find all the critical points in increasing order and determine whether each of those critical points is a maximum or a minimum. No problem. First derivative sign test tells me all of that. So I go ahead and I take the first derivative. It's pretty straightforward, just the power rule all the way across. But then after I take that first derivative, I notice I have a cubic function set equal to 0. In this one, it's not bad to factor, because you can just group the first two and you can group the second two and factor this by grouping. When I group the first two, I can factor out a 5x squared and it leaves me x plus 4. When I group the second two, I can take out a factor of negative 45 and it'll leave me x plus 4. So then you say, well, clearly you have a common factor of x plus 4. When you factor that out, you'll be left with 5x squared minus 45. That 5x squared minus 45 can be further factored. You can factor a 5 out of it, and you'd have x squared minus 9. And then, of course, we know x squared minus 9 factors by difference of two squares to x plus 3, x minus 3. Okay, now this is my fully factored form of that derivative f prime of x. You set each factor equal to 0. Clearly, the first factor can equal 0, but all the others can. So x plus 3 is equal to 0 when x is negative 3, x minus 3 is equal to 0 when x is 3, and x plus 4 is equal to 0 at x equals negative 4. These are my three critical points. So notice my first derivative sign test over here. I broke up the domain of the original function, which is all real numbers, from negative infinity to infinity, with these three critical points. So you say from negative infinity to the lowest critical point, negative 4, that low critical point, negative 4, to the next one, negative 3, then from negative 3 to 3, and then from 3 to infinity. Those are my four test intervals. I chose test points within each one. Negative 5 fits in the first interval, negative 3.5 in the second one, 0 in the third one, and 5 in the fourth one. Now, these test points get plugged into your first derivative. It's much easier if you'll use the most factored version of that first derivative in order to determine whether your first derivative is positive or negative at each of these values. So I went ahead and put the factored version. Clearly, 5 is always positive. It's a positive 5. But then I just went in factor by factor, and I said, well, if I'm plugging in a negative 5, the second factor here would be negative. If I'm plugging in a negative 3.5, still negative. If I'm plugging in a 0, that second factor is positive. If I plug in a 5, clearly it's a positive. It'd be a positive 8. When I go to the third factor, negative 5 minus 3, negative. Negative 3.5, that'd be negative 6.5, negative. A 0, still a negative. And I plug in a 5, it'd be 5 minus 3. That third factor would be positive in the last one. When I go to my last factor, x plus 4, if you plug in a negative 5, clearly it's a negative. If you plug in a negative 3.5, though, it'd be a positive 0.5. All I care about is the sign. I put a positive. You plug in your other two values, 0 plus 4 and 5 plus 4. Clearly, those last two give me a positive factor there. Now, in order to determine the sign in each interval, I just multiply across. I can say, well, I know that 3 negatives make a negative. 2 negatives make a positive, 1 negative makes a negative, and the product of 4 positive numbers is positive. So this tells me that my function is decreasing from negative infinity to negative 4. Then it's going to be increasing from negative 4 to negative 3. Anytime you change from decreasing to increasing, you're going to have a minimum at that critical point. So you'll see I said there was a minimum at negative 4. And then I'm going to be increasing up until negative 3, but then I see decreasing after negative 3. That means you're going to have a maximum at negative 3. Anytime you change from increasing to decreasing, you're going to have a maximum. Then it's decreasing from negative 3 to 3, so it's going to keep on coming down until I get to till positive 3. And then it's going to increase after positive 3. So I know positive 3 is, again, the location of a minimum. So now as I go through here and try to answer the problem out, it's saying using decimal notation, we won't have to round to 2 decimal places. These are exact values. Write the critical points in increasing order. Well, the first critical point you come to is negative 4. So I'll say, okay, here I have a negative 4. What do I know about negative 4? I know negative 4 is the location of a minimum. So now I scroll on down and it'll say, well, what's your next critical point? Well, the next critical point was negative 3. And I know at negative 3, keep in mind, the function was increasing until negative 3, decreasing after. Negative 3 was the location of a maximum. So I can say, well, there's a local maximum there. My next one was at x equals 3. And we know that that, again, was a minimum. And then it increased after that on off to infinity. I can check this answer. Better be correct. And it is. Hopefully that helps you out with the logic required in this problem. It's the first derivative test, a pretty important concept from our class. Make sure you see what I did in that chart and why. It really is a neat and hopefully you'll think fairly easy topic once you get accustomed to these problems. Let me know if you have any questions.